Good morning, or good afternoon, depending on where you are. We are continuing with our thermodynamic lectures, and today we want to look at forced convective transfers in a turbulent boundary layer. So we want to see forced convective in a turbulent layer. We have already talked about turbulence. That turbulence are the result in fluid flow as a result of velocity gradients which develop within the fluid flow. And as a result of these velocity gradients, we have eddies. And these are basically non-linear forces. They are not directional. It's very difficult to predict their behavior, both in terms of their positions and locations and quantities and so forth. But then we used the concept of Reynolds decomposition, where we have an expected value. So if we are assuming that we have an expected value, and we have mean value of these properties, and these mean values cancel out. They cancel out. And so when we are dealing with the turbulent entity or boundary, then it is very difficult to develop analytical solutions in terms of, for example, the heat transfer in a turbulent layer. That's not that difficult to develop analytical solutions for heat transfer, for example, in a turbulent layer. And the other thing which we need to take cognizance of is you can make an assumption like the one which was thought of by Reynolds. We assumed that there is a similarity, there could be a similarity between heat transfer, but there could be some sort of a similarity between heat transfer in these turbulent systems to friction in liquids. So we can assume sort of similarity between heat transfer in a turbulent layer to friction in liquids. Now, when you get a hold of that assumption, where you're assuming it could be related to friction in liquids, then it means that probably you can get some solutions based on hydrodynamic measurements, like, for example, the viscous drag of that fluid on a surface. Therefore, there is a possibility. This opens an avenue, therefore possibility obtaining solution from hydrodynamic measurements. A good example is viscous drag of fluids on surfaces. Now, let us work with a model where we look at the fluid flowing across a boundary. Let us develop a model to try to explain this convective heat transfer in a turbulent layer. But we start off by developing a model where we have fluid flowing across a boundary, flowing across a boundary, and we assume that there's a region where we have shear stress, and so in that particular region, we are assuming that there could be mass transfers and there could be transfer of momentum, whether it's through macromolecular or molecular carriers, whichever way, to the wall, normal to the wall, and so forth and so forth. Those we have mentioned when we are talking about developing concepts in turbulent boundary layer. So again, always, as I always encourage you, please check those things so that we are all together and we build up. So we develop a model. Let's develop a model first and see if we can correlate those quantities as you have said. Now, let's look at our model where we have a fluid flowing across a boundary. So we have our there. Remember, in our postulates on the development of concepts in the turbulent boundary layer, we resolved our velocity in two directions, x and y. That is y, and that is x. And we associated y with the velocity v, and x we associated with the velocity u. So we resolve it into two components. Now, and in that resolution of velocity into two components, don't forget, we said that the instantaneous velocity is the sum of the main velocities and the velocity resulting from fluctuations in this turbulent region as a result of those eddy motions. Now, we have that. So we have let's say that this is stream velocity. It's our boundary layer, boundary velocity. You're already familiar with these quantities. So we have our velocity profile. Let us say that this is the turbulent region. It's the turbulent region. And let us say that this small section, let's denote some small section here. And say that we have shear forces, tau. This is shear stress. Shear stress. Tau. And so what are we saying? We had said that in this shear stress region, there could be material transfer or transfer momentum. But let's call this region, let's call it Roman numeral 1. The region Roman numeral 1. So in the region Roman numeral 1, we have shear stress, and there could be transfer of material. Because remember, like we have always said, these are open system. You have transfer of material or momentum by macroscopic or molecular carriers. And so, what did we say? Then it means that stress in this region is twofold. We have that as a result of viscous forces and that as a result of shear stress. We developed that concept when we were talking about the turbulent boundary layer. So, what do you mean? So we had said that, so the shear stress, which we denote as tau, we know tau is mu du dy, and that is also rho mu du dy. And you know that this mu is dynamic viscosity, and you know that that rho of course is density, and this v there is kinematic. Viscosity. And so when we developed the concept of the turbulent boundary layer, we developed expressions which related the shear stress due to turbulence, so that the total shear stress was the shear stress due to viscous forces and also due to shear stress. So let us just, so we developed the turbulent region, where, remember, like we have said, we said that the V1 was V main plus V1 prime, where that was the mean velocity. This was velocity as a result of fluctuating velocities, as a result of the eddies. It's the fluctuating velocity. And that was the instantaneous velocity. Instantaneous velocity. And the same went for U. And we ended up with the expression where we found that the shear stress due to eddy, the eddy shear stress, was the mean of these velocities which are fluctuating. And so we equated this and said that we could express it as rho E du dy, where this E was eddy diffusivity. Please try to go through those lectures. We have discussed these things in details, but you have to pick up from there. You have to pick up elements of them so we can't rederive them again, because if you do that, then it will be quite a long talk. So some which you have covered, you just highlight them, mention them, so that we had this total shear stress. Oh, I might need that diagram, but just have it in your mind. If we need it again, we'll draw it again. So we just said that shear, the total, was shear due to viscous forces, and now due to the eddies. So we want to try the same model with heat conduction in this turbulent region. Remember, put that what we have discussed in terms of shear stress, and we want to use the same model to develop methods to compute heat, convective heat transfer in this turbulent region, So, what is our model? The model which we have, so we have to redraw our system again. So we say that was X axis, this was Y axis. Of course, this corresponds to V, this corresponds to U, and we had a velocity profile, turbulent region. We have our region, Roman numeral 1, which we say was where we have the shear, stress, and of course, we have our velocities, boundary, stream. Call it free stream or just call it stream. Now, we want to see if we can develop a model for heat conduction in this turbulent region. And always remember, the turbulence is a result of those velocity gradients in the fluid flow. So, suppose we say that the temperature, of course, remember always, even if you don't mention it, always remember that there's a laminar sublayer here. Next to the wall. Don't always remember that. And if you don't mention it, always remember there's a sublayer, some small layer where we have laminar. Now, suppose we say that just for illustration purposes, let us just say that we have the temperature here in this region. Let us call it T1. And let us call the temperature in this region, this is just for illustration purposes, T2. And one of the concepts which I've always said is that for heat to be transferred, there must be a temperature differential. So if we assume that the temperature next to the wall is higher than the temperature 2, let us put that down. If we say that the temperature, let's say the temperature T1 near the wall is higher than temperature T2. It's above boundary there. IA, so what are we saying? T1 is greater than T2. So because of that temperature differential, there will be thermal transfer. There will be thermal transfer. So when there's thermal transfer as a result of that temperature differential, we can use the same model which we used when we are developing the expressions involving shear stress in the turbulent region. And that model, just like we resolve the velocity into the mean component and the component as a result of the fluctuations, we can do the same for temperature. So we can develop the same model for heat conduction So let us say we have our heat that is cold eddies. We can call this cold eddy, cold eddy coming from top, hot eddy from bottom. And so we are saying heat for heat conduction. For heat conduction, we can assume that the instantaneous temperature is equal to the mean temperature plus temperature as a result of these fluctuations. We can assume T1 is T bar plus T1 prime, where again T1 is instantaneous temperature T2 is mean temperature, and this is the temperature due to fluctuations. In the other case, we were talking of instantaneous velocity, mean velocity, and velocity as a result, the fluctuating velocity as a result of those turbulence. They are non-linear forces. Now, let us proceed in the same direction. Now, the mass flow per unit area in that section where we're having turbulent, which we have called Roman numeral 1. I don't know why I keep erasing it, and I keep needing it. I keep erasing it, but I need it. Let me just draw the Roman numeral 1 region. So we have the Roman numeral 1 region. So we are saying that if we look at this particular region, the mass flow per unit area over some time interval dt will be given as the mass flow per unit area over a time interval. Let's call that interval dt. Over time interval, let's call it dt. So that particular quantity will be given by the density times the velocity dt. And so in terms of energy, if we talk of in terms of energy, then we now know that we simply multiply by the heat capacity and the temperature change, because remember, dH is simply Cp dt. So in terms of energy, we have that as rho V1 dt Cp T1. So if we take this quantity of a longer interval, let us call that interval time interval P, where P is much greater than dt, computed over a longer time interval, P, where P much greater than dt. In fact, let's call it T instead of P, just to be consistent. T, capital T instead of P, much greater than that. Then we can integrate over the interval. We can do integration over the interval. Therefore, integrate. This we have done. So I can integrate this quantity, and that is representative of the heat flow. We have heat, Ed. We have the integral, so T rho V1 dt Cp T1 Cp dt, because we divide by that time interval. And so remember, we have already said that V1, we know, is the main velocity plus the velocity as a result of the fluctuations. Because remember, we are modeling basically like we dealt with our earlier expressions involving turbulent regions, where we resolved the velocities into their components, and we have the mean velocity and the velocity as a result of fluctuations. So in the same way, temperature 1 is also resolved into the mean temperature, which we had already indicated, and temperature as a result of those fluctuations. So if we put this in the expression there, we can remove rho, that is density, and the isobaric heat capacity outside. So we have rho Cp. Now I don't need this, let me use this side. So now, if we move there, we now have rho Cp over P integral 0 to T. We put in the values for V1 and T1. So we have V1 prime and T1 plus T1 prime dt. So for these quantities, what do we have? If you open up this bracket, V bar, V1, the mean velocity and mean time, mean temperature, we have V bar 1, T1. I'm just dealing with that section there. Then of course we'll have plus V1 bar T1 prime plus V1 bar T1 prime T1, the mean, plus V1 prime T1 prime. And as you have already mentioned, as you mentioned in our earlier derivations, when you're dealing in steady flows, then you find that this V bar 1 is negligible. So what does it mean? So it means that those quantities where we'll have Cp, the integral, for example, let's just say the integral. So what does that mean? What does that statement mean? It means the integral of V bar 1, T bar 1 is 0. All these quantities, the integral of V bar 1, T1 prime is 0. And the same with the integral of V1 prime T bar 1 is 0. Because we told you that those quantities which fluctuate, we have the expected value, but the ones which fluctuate, they add up to 0. Remember that? Please just go through our earlier lectures with those turbulent bounded layer kindly. Now, so that in a nutshell, the integral which we are left with will be this one here. So we will have rho Cp over P integral from 0 to T for V1 prime, T1 prime. This we say this is T, not P. We said that was T. Remember? That was T. Wherever we put it, that was T, remember? And so we end up with this quantity, rho, this will be rho Cp V1 prime T1 prime for Q. And remember, this was the same, almost the same expression we had for the shear stress. This expression here is about the same expression which we had for the shear stress expression. And so we have this quantity here for the expression for the heat conduction through that turbulent region where we have shear stress as being given by that. Remember, in the case of shear stress, recall, in the case of shear stress, we had minus rho and the mean of the velocities, and that was equals to rho du dy, where we say that was AD diffusivity. And so we can also bring an element of diffusivity into this particular expression. If we remind ourselves, like we had done in the other, like we had seen derived in the earlier lectures, where we derived the thermal diffusivity, which was part of the Fourier number, we had said that alpha, which was thermal diffusivity, was K rho Cp, where alpha is thermal diffusivity. And this, remember, was in the Fourier number, where we derived the Fourier number and Biot number. And so we can bring that in there. Instead of rho Cp, we clearly see that instead of rho Cp, because we say that is thermal conductivity over rho Cp, so alpha rho Cp is equals to K, and so rho Cp is equals to K over alpha. So we can plug that here. We can plug that in this expression so that Q Ed is now rho Cp